Good afternoon and welcome to Binghamton University. It's a real pleasure to have you all with us here today. I'm told that this is our 5th Innovation Day, which is really exciting. It's starting to become a really big annual event. We have 159 people registered for the conference this year, which is really fantastic. It continues to grow every year. And this all started in 2012. So it's relatively young, but at 159, I think this is outstanding. I don't think we have 159 quite in the room yet, but probably people will show up. So what I thought I'd do is give you a quick introduction to research at Binghamton University with really an eye towards innovation and technology transfer. So that will be my focus in this talk. And I'm going to take about 10 to 15 minutes at the most, or less. So the research division at Binghamton University has the vision that our research is going to help the university to achieve becoming a premier research university. We also realize that our research needs to be transformational. It has to have an impact on society. And the best way to do this is to work with industry. So from our perspective, working with the community at large, industry in particular, is the best way to make sure that our research is applied and useful and has an impact on society. Our goals are to increase the research, scholarship, and creative activities. We want to increase them with quality. We want to become a premier public university and to be nationally recognized. We also want to increase the transformational impact on society. And as I said, the best way to do that is to work with the community, whether it's private sector, national labs, or hospitals, and the community at large. We support and promote a culture of consciousness and responsibility, and we value and really pay attention to diversity and inclusion. So these are things that are at the core of everything that we do. They're integrated in the way we do business on campus. So by conscious and responsibility, I'm talking about compliance, research ethics, research care, and then diversity and inclusion are things that we care about in hiring, in embracing people and bringing them on campus and making everyone feel that they're welcome and that they're at home. These are really key values that we have. And finally, our division also advocates for the campus needs with regional, state, and national representatives. So both state and federal government relations are in the research of division. So these are the key parts of the research division. The metrics for the research division are, we measure a lot of things. I'm going to show you a very small section of what we measure. One key thing for us is external funding. The reason is that we are a not-for-profit, which means that our expenditures are equal to our to what we bring in, to committed funds. The two have to match. We have to net things out at zero. We can't overspend or underspend. If you look at our committed funds, they had been coming down for a number of years. You can see this. This is the end of a multi-year trend. That was a reflection of several factors. One of them is we were not hiring new faculty. We were actually shrinking in size with time due to budget cuts. It also reflects the end of appropriations, which were directed funds. We did extremely well with appropriations. And it also reflects the end of the American Recovery Act. So all these things caused us to shrink in size, to shrink our research. We were not alone. All of SUNY shrank in size considerably. And across the nation, most universities were shrinking in their research during this period. What has changed for us, the trend we're on right now is a very healthy trend of growth. And that's because we've been hiring faculty. We've hired a net growth of 125 faculty over the last 4 years. Our total hiring was more like 250 faculty, but about half of that was replacement. So we have grown significantly. We've added a School of Pharmacy, and we've grown in almost every area, but with a focus on areas that are transformational and likely to yield a healthy growth. So engineering is growing, and basic sciences are growing, and many other areas. And then the School of Pharmacy is a whole new area that we just started. And if you look at our committed funds last year grew by more than 20%. Year to date, we're on the same trend. We're growing at about 16% this year. Expenditures typically lag a little bit. Faculty like to store some funding for rainy days. We've had many rainy days in the past, so they're being cautious. But hopefully this will pick up as well soon. And we've set a target of hitting $50 million a year by the year 2020. That's a very aggressive target, and we are confident that we will be able to accomplish that. In terms of research expenditures by sponsor and topic, we're always paying attention to federal funding. That's the most important part of our funding. It's the most competitive funding. So this would be NIH, NSF type of funding, DOE, DOD. So about half our funding comes from national sources. We also pay a lot of attention to funding by the private sector, so industry and small business, which is about 8%, and that's significantly higher than the national average. So this is the piece I said earlier that we really care about. We care about this because of two things. One of them is it makes sure that the research is transformational and somebody will benefit from it. Number two, having industry with us when we apply for federal funding improves our chances of winning. So it really, both go hand in hand. In terms of by topic, I should point out that healthcare, neuroscience, and nursing is a very significant piece. Energy and electronics packaging are other really important areas for us. And many of these are correlated. Electronics packaging fits really well with energy and with national security and information security. So many of these areas feed on each other. We invest heavily in our faculty. So I just mentioned we hired 125 faculty, new faculty, net growth over the last 4 years. And you can see our investment in research infrastructure, startup funds for those faculty have almost quadrupled over that period. So we used to be at less than $1 million a year about 5 years ago. That was our total budget for startup. We're now at about $3.5 million, and we are probably at the end of this big hiring spree. From now on, we'll have more selective, slower hiring over the next few years. The intent now is to start growing our graduate education, the graduate students, so PhDs and masters rather than undergrads. Undergrads will remain at their level. And the other thing I should point out is we did grow from about 13,000 to 17,000 over the same period. While we did this growth, our SAT scores continued to remain very high, very strong. We have outstanding undergraduate students. I should also point out that the growth in the graduate side was slower than the growth in the undergrad, but the faculty ratio, overall faculty to student ratio actually improved during this growth period because of the hiring on the faculty side outgrew the student side. In terms of technology transfer, we had a great year in 14-15. We had a record number of patents. Our technology disclosures are high and continue to be robust. We generated about $500,000 in royalties, and we have 11 companies in the campus startup suite. Some of the companies are faculty startups, others are from the community. And we're, again, looking at that number carefully and hoping that will continue to grow. 5 years ago, Binghamton University did not lead any federal centers, federal research centers. By that, I mean centers funded by either DOD, DOE, or NSF, NIH. And today we have 4 federal centers. One of them is this is a New York State node of one of the NMI's national manufacturing initiatives. This one is on flexible hybrid electronics. It's the most recent of the NMIs that have been announced. And Professor Mark Pollux is the leader of that node. And he can raise as much as $40 million in total over the next 5 years. And that funding is half federal and half state. So New York State provided a $20 million match. So it's a very exciting project. It looks at building electronic systems on flexible substrates with the integrated thin, flexible silicon on it. So you can think of many applications in things like displays or health sciences or wearable electronics, just tremendous applications. The other federal center we have is the NACSES, which is the Northeast Center for Chemical Energy Storage, led by Stan Whittingham, who I believe is here and will be presenting to you shortly. And that's a really prestigious center. It's about $13 million in funding. And it's to look at lithium-ion batteries and find ways of restructuring the materials that make the battery at the nanoscale in order to be able to increase the energy density. So this potentially can result in significant increases in the energy that's contained within a certain volume or weight, which means your cell phone can run for days instead of one day, and any portable electronics can run longer. This would have an impact on every aspect of our lives, including electric cars. Everything would be impacted. So really exciting research area. And we have this center because of Stan, because of his international reputation in the area of lithium-ion batteries. He's one of the co-inventors of the first disclosures and papers that came out on lithium-ion while he was at Exxon before coming to Binghamton. Professor Linda Spear has a federal center on alcohol addiction. She's a professor in psychology, and that's an NIH center. Again, another world-class scientist conducting outstanding research. And finally, Professor Kanad Ghosh leads an IUCRC, which is funded by the National Science Foundation, and that center is focused on reducing the energy consumed in data centers. Data centers use about 3% of our electric power in the United States, and about half of that is waste. So if we can recover 30 or 40% of that waste, it would be a really significant amount of energy. And that's all done through developing intelligent systems that can control and run data centers more efficiently without sacrificing performance. We have faculty, some of our newly hired faculty who are outstanding young faculty who are winning career awards. Career awards are sought by everyone in every university around the nation. Here are two examples, one from mechanical engineering and one from physics, working on very applied, very interesting, very exciting research that can really transform the world as we know it. I mean, really fundamental work. And again, the likelihood of winning a career award is probably less than 10%. So again, you know that our faculty are, the hiring we're doing right now is outstanding. Research across the disciplines, a couple of examples. One of them is Sean Choi, who's in electrical engineering, who's developing these paper batteries. You can see the origami nature of that battery, and you can think about all the applications, lightweight. You can develop it into wearable, portable, all kinds of different applications. And the idea would be very lightweight, efficient batteries that are inexpensive, almost disposable. And then Professor Angelo Mastrangelo in the School of Management, who is an entrepreneurial leader on campus, just wrote a new book called Entrepreneurial Leadership. And he's always been leading in areas to generate new business and to educate students on how to be entrepreneurs and think like leaders. Looking ahead, as you know, the Southern Tier won the URI, the Upstate Revitalization Initiative. This initiative will definitely make a huge difference to the Southern Tier. We're engaged in a number of projects related to the URI, including the Health Sciences campus in Johnson City. I would say that's the biggest thing for Binghamton University right now, is transforming Johnson City through the School of Pharmacy, and also moving the School of Nursing, and preparing space for companies to come and be able to conduct research and to manufacture in Johnson City. So it's really, over time, it will take time, but over time, we expect that this will completely change the texture of Johnson City and lift the entire area. Very exciting opportunities there. In terms of Startup New York, you're probably all very familiar with this program. So far, we have 13 companies that have been approved for the program. 8 of them have entered the program, and 7 of them are in our incubator on campus. And one of them is in downtown Binghamton. So it's a program that is just starting. We think that it's taken a long time to happen and to start kicking in, but we definitely have seen a big interest in startup companies since the program was announced. We're also building an incubator in Binghamton on Holly Street. It will be 21,000 square foot net space. And we usually show the picture of the incubator. Now we can actually show the incubator under construction. It will be completed by May of 2017. So we expect our companies to be able to move in by 2017. And we're working with a number of companies to make sure that the day the incubator is opened, Per will make sure that it is half full by that day. And he's nodding vigorously. And I'll stop here. I'm happy to take a couple of questions. I think I ran over my time by a little bit, but if you have any questions or comments, I'd be delighted to engage with you. Yes. Yeah, that's an excellent question. I mean, you can do it in one of two ways. You can start from the fundamental research perspective and make discoveries, and then look at your discoveries and wonder how they can apply, how they can be transformed into products and applications that people use. And we have some outstanding faculty that do that. A perfect example is psychology. So we have faculty in psychology who do really outstanding research. They're funded federally. They publish in the best journals out there. And then the work is available and other people transform it. And we also have faculty who start with applications. They start by thinking about, for example, if you think about flexible electronics, their whole drive is to think about a killer app. What is a killer app that if we can make it at this cost, people will buy it and use it and will become transformative. And then they start from that point and then work their way back to the technology and figure out what are the missing gaps that we need to work on. So you can do it both ways. You can start by looking at the apps, or you can start by looking at the basic research. And then in the end, the idea is to reach a manufacturing perspective. And our faculty really do both. We cover the entire gamut. I think at Binghamton, if I think about all the projects we do, I think we would be probably 60-40, 60% being people who are working with industry already and are thinking about applications and usage, and maybe 30 to 40% of people who are thinking about fundamental questions and trying to answer them, and then at that point, look, are there ways to transform it into products and applications that people will use? And with that, I'll thank you, and I would like to introduce Professor Kai-Ming Yi, who is the chair of our biomedical engineering department. And if I read you his qualifications and his bio, it would take another 15 minutes, but we did make a copy of it, and I think it's in the packages. Professor Kai-Ming Yi is an internationally known leader in the area of regenerative medicine.
Thank you, Buket, for your very nice introduction. All right, so in the next maybe about 40 minutes, I'm going to share some of our research work, and particularly building the islets like the organoids and from the iPS cells. If I have another 5 minutes, I'm going to share with you our recent activities, particularly try to build a National Institute for Advanced Biomanufacturing. Actually, we just put a team together from different part of the state, and also put all this partner with the industry and form the team, which is submit the proposal to the NIST and competing for their National Institute. All right, so let me start from the this kind of picture. Let me go out here. Okay, so this is basically one of the slides and highly summarized what happens in my lab and what we want to accomplish. And basically what we try to accomplish, that's basically the end goal, is to develop the cell and tissue-based therapy and use all kind of start from all kind of cell sources. We work on using my early work more focused on using the adult stem cells, using the adult somatic stem cells or adult cells, and build those on different cell types. And we're particularly interested working on the pancreatic cells that's related to can be used for the diabetes treatments. And in the last 10 years, my work more focused on using the embryonic stem cells. And lately we switched from embryonic stems to the iPS cells, because iPS cells can be produced and reprogrammed and from the human adult somatic cells. And this is basically show you the very, it's the all kind of cells, even skin cells and neuron cells and liver cells, blood cells can be all generated from iPS cells. This is basically particularly my lab's more particularly interest in diabetes treatments. And for those who are not too much familiar with their diabetes, and I'm just give this kind of very quick and briefly on slide sort of the introduction. What's the problem for diabetes for diabetic patient? And there's a type 1, type 2 on diabetes. For type 2, and usually there's a patient, they have beta cells in their body. They can generate, there's a patient, they can generate they can produce the insulin in response to the rise of the glucose concentration in the blood. However, they're on the body, particularly skeletal muscle cell, does not respond to the insulin and bring down the glucose concentration in the blood. And particularly for those patients in the late stage, and you will observe there is significant loss of the beta cell mass in their pancreas. Therefore, just like a type 1 diabetic patients, the transplant or implantation of the transplant to the beta cells, which we call the insulin secreting N cells, is the ultimate treatment for those patients. So for type 1, that's very clear. It's the only cure is the beta cell transplantations. And this is to give you some idea about what's happening in the pancreas. If you look at, and this is basic islets, it's a cell clusters. It consists of the 4 different type cells: alpha, beta, delta, and PP. That's basically pancreatic polypeptide cells. And particularly important is the beta cells. So beta cell is type of cells, they secrete the insulin in response to the rise of the glucose concentrations. And this panel, this slide just show you what's happening in the type 1 diabetic patients. And this is a very healthy islets. You see that you have a critical mass of the beta cells. So this basically show you for type 1 diabetic patients. And the green, this one to show the green labeled as the T cells, and the red is the beta cells. You will see, and there's a T cells start to infiltrate and basically invade into the pancreas and destroy the beta cells. You see the later stage, you see the significant loss of the masses of the beta cells because of attack of the T cells. Well, in the last almost decades, 2 decades, and there's tons of the money spent by NIH and try to understand fundamentally what's the mechanism. We still don't know. After 30 years of very extensive study, we still don't know what happens, why the T cell will attack on those the beta cells. So now the solution in today to deal with this kind of situation is to, since we don't know how to prevent it, we don't know how to reverse the causes. And the way to do it, and basically, is to generate the iPS cell, and then we can generate the insulin secreting beta cells. Then we can, if we transplant those beta cells in the patient, and then you can restore the patient's physical insulin secretion capacities. And this panel pretty much summarizes what has been done, what has been attempted, particularly in people try to using the, the goal is try to generate these beta cells. And these beta cells, they can secrete the insulin. That's what's required for on those patients. And these are basically the cells, people start from different source of the cells. They've been using the stem cells, particularly to adult stem cells. And people has been trying use the, liver, bone marrow, gut, and blood cells, and even they're using the beta cells themselves, try to proliferate those beta cells in the bioreactors. They increase the number, then you can transplant those beta cells into the patient's body. But all those attempts, all those try, has generated some very limited success. In other words, the beta cell generated from those sources, they have a very limited capacity of the insulin secretions. They can secrete insulin in response to the glucose, but when you transplant the cells into the body, and the cells do not respond to the blood, the rise of the blood glucose concentration, the rise of the glucose concentration in the blood. In other words, those cells are like the beta cell, but they are not actually the beta cells. So in the last 10 years, people almost conclude, and that this basically try to start from adult cells to generate a beta cell. That's the dead end, and I pretty much cut all the fundings and to support this kind of research. All the focus and switch to the ESL and later on as iPS cells, because ESLs, embryonic stem cell, are supposed to be able to differentiate and generate all kinds of cells in our body. Now, before we figured out how to generate, how to produce this beta cells from, and the embryonic stem cell or iPS cells, we need to look at the biology. That's what we're doing for the engineer. We need to look at the biology. We need to look at what's happening and during the embryo developments. And this is basically all the knowledge today we have on the beta cell development from the embryo or from the mouse, because we cannot use in the human embryo to do the study, but we can use the mouse embryo and try to dissect and each stage and understand on the mechanism. So based on this study and almost 10 to 15 years of study, now we understand, for embryo developed, mature into the beta cells, basically here, that says 2 waves of the differentiation occur. So very critical, that's 2 different waves and 2 waves of differentiation occur during that courses. The first wave is basically to embryo develop into the pancreatic, which we call the endodome structures, pancreatic endodome structures. And that happens in the mouse, and basically happens in the close about the 10 weeks. Then after this first wave of differentiation, the second wave basically is maturation. It's to further mature and generate the basically islet cells from those endoderms, pancreatic endoderms progeny cells. So now, and also by analyzing this process, now we understand the developments is not basically happen in a one sequence, it's a stepwise. Then this is on slide pretty much to analyze the gene expressions. How does the gene expressions and sequentially and reflect the stepwise differentiation process? Now, this is basically show you all the differentiation is branch-wise, and you have some key genes. For example, for the first wave, at the end of the first wave of differentiations, the PDX1 expression in a very high level in those pancreatic endodermal progeny cells. So afterwards, you will see the gene expressions start to branch out, and for those cells differentiate toward, and this is basically pancreatic endodermal cells, and this is those cells basically toward the exocrine and the lineages. Basically, it's the pancreatic exocrine. So, and one of another key gene expression is basically is the MIF-A. So for those cells start to differentiate leaning toward or mature into the beta cells, those cells express the MIF-A cells. Because MIF-A genes do not express in the alpha and delta and also PP cells. So that's basically is another by analyzing the key gene expression in the several stages. Now we understand the process. So by understanding the process, now it's the ways to how to use engineering approach to really mimic this in vivo stepwise differentiations then will be achieved in the differentiation or generating, producing these beta cells from the iPS cells. So now, this is basically the protocol was developed by the DLMO groups in about 2000 and from Stanford. So they basically recognize, they divide the entire and the embryonic development process into the 5 stages. It's a stage 1, you're from the embryo develop into the definitive endodermal, then from the DE and further develop into the primitive gut tube, and this further go to the posterior foregut, and then branch out to the pancreatic endodermal, then further mature into the islets. So this is the 5 major steps they identify what's happening during the embryo development into the islets. So now, in order to mimic this situation, they divide into the steps, then because they're using the different sets of the growth factors. What they did is using different sets of the growth factor to control each step of the differentiations. For example, when they try to control the differentiation of the ES cell into the definitive endodermal cells, they use the 1 set of the growth factors. And in order to differentiate from the DE cells into the primitive gut tube, they switch to another set of the growth factors, then switch to another growth factors, another sets of growth factors. By using the different sets of the glucose combination of the growth factors, they will be able to very precisely to control the differentiation of the embryonic stem cells stepwise toward and basically pancreatic cells. So now they're very successful, and they succeed in generating the insulin secreting cells and at the end of the differentiations. And however, we review the reference and we look at the data. So if you look at it here, so only 7% of the cells are insulin secreting beta cells at the end stage of their differentiations. So now, what does that mean if only 7%? That means if we want to use this approach to treat one single diabetic patient, we need a bioreactor. We need a bioreactor just like a football size. We need a football size bioreactor, only treat one single patient. So, and that's what we always call is a very successful science discovery. It's very successful science discovery. Now we show we can generate the beta cells. However, it's not practical. You can't not apply this approach and really to treat a patient because you need to build very, very large, gigantic bioreactors in order to supply producing the beta cells for patient treatment. So the second and the problem with this approach is the beta cell, the biological function of the functionality of the beta cells. They tested the beta cells, they challenged the beta cells and upon a glucose. When using glucose charge, they see the cells start to secrete the very limited level of the insulin, but not C-peptide. We all know C-peptide is a pro on insulin products. If the cell do not secrete C-peptide, and then pretty much the cell are not mature enough. And that's exactly what happened when they transplant the cells in the mouse, and the cell work in the first couple of weeks, and after a couple of weeks, the cell just stop responding to the rise of the glucose concentration in blood. So there's 2 problems. One is the number of the cells, beta cells, are very low, and at the end of the stage of differentiation. Number 2, the functionality, the maturity of the cells are pretty low. So we need, in order to improve these situations, we need to come back with another approaches. And I want to skip this one. So what we did basically this is basically the experiment that was done 5 years ago, and I asked my PhD students and work with one of my postdocs and try to find out what's going on. And they basically look at the biology, see what's happening inside on the body. So if you look at this slide to show you, if you look at a cell to cell, this cartoon to show you the cell in the body, they're not just basically isolated. They're not just floating around in the bodies. They basically interact each other. It's called a cell-cell interaction. They interact each other through called ECM. That's called extracellular matrix. So extracellular matrix and provide the, and the framework allow the cell-cell interact and also cell interact with the ECM, that's called extracellular matrix. In other words, if you look at it here, the cells basically are exposed to two different sets of the signals. One is the soluble signals. That's what the people has been DMOS group utilized to control the differentiation of embryonic stem cell into the pancreatic cell. They use the growth factors. Because the growth factors, cytokines, chemokines, small molecule, there are soluble signals. You can add them to the cell culture medium to control the differentiations. However, in this approach, and missing another set of the signal that's called insoluble signals. And that signal is provided by the ECM, that's extracellular matrix. And also, and the signal is basically mediated by the cell-cell interaction and physicochemical cues, that's basic electrical, mechanical, and also topological structure of the ECM. So we basically analyze, we say, okay, the reason for the failure of their approach is because they're missing another parts of the signal, another half sets of the signal are missing from their approach. Now the question, how do we create on these environments allow us to provide both the soluble and insoluble signals? So we came up with a very simple idea that's called 3 cultures. So we look at, because the reason they're missing insoluble signal because they're using this 2D cultures. What happened, I asked my postdocs, what happened if we just grow the cells and differentiate the cells in the scaffold? Then scaffold and play the role just like function as an extracellular matrix, allow cell to interact with each other, allow the cell to interact with the ECM. So it's a very, very simple concept, very simple technologies. And then this will basically show you the, the approach we use. In my lab, we use the decellularized material, we use the synthetic material to fabricate, and there's a scaffold. We also use the 3D printing technology and to print the scaffold and also deposit cell in the organized structures. And then we also work on the organ chip and building a system for drug testing. Now I want to skip this detail. This is just give you the, by understanding the process, now we need to pick up the system. So in the beginning, we choose the very simple system as a mouse embryonic stem. The reason we start from mouse embryonic stem cell was much easier to play, it's cheaper. So just for the proof, the concept. And this is the protocol we used, and to show you some experiment data. And thanks, how much time do I have? Again, Laura, how much time do I have? 20 minutes? Okay, I'm going to go quick. And this is to show you the experiment result, and which we did. Basically, the first step we want to see if the cell can grow inside of the scaffold. And can grow, and you see this is the day 1 and day 3, day 5, day 7. You see the cells start to aggregate and form the very nicely uniformed embryo body. And that's embryo body is indicating the cell start to aggregate, start to assemble into tissue structure, start to grow. Now this is also show you the detail. We're using the SEM and the SEM scanning microscopy and to study the detail. This is show you the structure, the detailed structure of the scaffold, and they show this, the diameter of the fibers of the ECM is very uniformly, and porosity also very uniform. And then this is show you the, I think this is very difficult to see. This is a basic embryo body, and this is also another embryo body. So we see there's a size. I can show you another side with much easier. Yeah, here's, okay. So this will give you the detail. This is a very 3 different embryo body formed and inside the scaffold. You see they're very uniformly, the size and morphology, they're very, very much uniform. And also you see here, we start to see there's 2 on embryo body, they communicate each other, because this is the basic ECM. And this ECM secrete from this embryo bodies to communicate with the embryo body far away. So that's the very exciting discovery, and we show, and the 3D cultures really encourage cell to form and very uniform, well distribute the embryo body, and they start to communicate each other. Those communications should improve or encourage the cell and secretes and become mature. And now we basically, then we did go all the way to the end and start to differentiate those cells into the beta cells. And we're using the very simple approach, which is the DTZ staining, to see how many beta cells are generated. And DTZ is kind of dye that only stain the cell which contain a very high concentration of zinc. So any cell for insulin producing cell, they usually has a very high concentration of the zinc. So by staining, by performing the DTZ staining, we'll be able to see how many insulin cells are generated at the end of the stages. So if you look at this data here, we observed that 46% of the cells, 3D differentiated cells, are insulin positive cells, and only 7% of cells are insulin positive when they differentiate on the 2D environments. And this data is very consistent with the report which you see on in the literatures. And that's basically very powerful data to show you just simply differentiated cells in the scaffold. So we'll be able to increase the insulin secreting cell from 7% to 46%. It's almost about a 6% of the 6-fold increase. And then we basically use the antibody. Now we do the more detailed detections. We're using the anti-insulin, PDX1 expression, and also glucose transport 2. So the reason we choose the glucose transport 2 gene, protein expression, and also PDX1, so because glucose 2, PDX1 are 2 hall markers for the mature beta cells. And here, this is basically on this panel showed you the adult islets, and this is 3D differentiate from the islets. This is the 2D from the cell islets. If you look at all this marker, the purple is a DABI staining the cell nucleus, and the red is the anti-insulin. That means those cells secreted insulin are beta cells. See the 3D form the cell clusters and show the very similar morphology you can see in the adult islets, and 2D does not show this kind of morphology. And that's basically a clear indication on the 3D differentiation really provided environments allow the cell to assemble into the islet structures. We also did the C-peptide staining, and we see, again, this is the adult islets, this is the 3D form, the cell cluster, this is the 2D form, the cluster, this is basic negative control. So again, we observed, and by performing the C-peptide staining, we see the cell formed on the islets like a structure and under the 3D dimensional, 3D cultures. We also did analyze the gene analysis that time. I did not have the real-time PCR. I just basically did simply on RT-PCR, and that's why we call it a semi-quantitative approach to analyze the gene expression. Again, this is we choose the key markers insulin gene, PDX1, glucose transport 2, and those markers. And this is basically adult expression of those genes in the adult islets, and this expression of the gene in the 3D form the cell cluster. This is in 2D form the cell clusters. You see the expression of those key marker, pancreatic or key gene markers in the 3D form the cell clusters at the same level as you will observe in the adult islets. And that's basically indicating those cell clusters are mature, their maturity very close to the adult islets. Then we perform the glucose challenge. We challenge the cells with the glucose to see if the cells secrete the insulin. You see this is a 2D and a 3D. This is basically how much insulin secrete upon a glucose challenge. You see there's a 3D form the cell class that secrete a much high level of the insulin compared to those cells and secrete compared to those cells and differentiate on the 2D form the clusters. Then we switch from now we know the protocol works, the approach works. Now we start to test the human embryonic stem cells. And this is basically show you the protocol and basically to use control the human embryonic stem cell into the beta cells. And this is basically the material we use. We use the collagen and also the matrigel. We also added a different concentration, the ECM, and to further promote the human embryonic stem cell growth. And I show you some data. But the other when we work on the human embryonic stem cell, we discovered one of the growth factors called the indolactin M5. And this is a very unique growth factors that appear played a key role in every stage of the pancreatic endodermal differentiations. So we want to see what happens if we combine these growth factors and the 3D cultures. So how those combinatory effects influences the human ear cell differentiations. If you look at it here, in the absence of these growth factors, we do the 2D cultures, we monitor the two and the key gene markers, one they call it PDX1, the other is HMF6. So PDX1 is the gene expressed only in the beta cells and also the pancreatic endocrine cells. HMF6, this gene will particularly express in the exocrine genes. So by monitoring gene expression, we'll see if you see in the 2D cultures without these growth factors, you see on cells express both the PDX1 and MHF6. That means there's a differentiation, the branch out, and really does not happen. The cell either differentiate toward the pancreatic endoderm or exocrine. So if your cell differentiate toward the exocrine, the cell will not generate the beta cells. So if you look at the 3D, if we combine those growth factors with the 3D, you see the cell, most of the cell express the PDX1. That means those cells will differentiate toward the beta cells. And in very few cells expressed on the HMF6, that means that these group cells are differentiate toward the exocrine. So that's basically indicating by combine the growth factor with the CS3D environment, we'll be able to control the differentiation specifically toward the pancreatic endoderm, not the exocrine on the pathways. Of course, this is also detect all those gene markers. We focus on the pancreatic markers. We see the 3D differentiated embryonic stem cell express much higher level of the pancreatic genes. And again, we use all kind of gene markers, and we detect the beta, delta, PP, and alpha cells in the 3D form the cell clusters. And that's indicating truly the islets like an organoid generated at the end of the differentiations. I don't know why it stopped working. Can anybody help me? Look like a frozen. Yeah, I cannot move forward. Yeah, okay. See, it doesn't work. Here's working. It doesn't work. Okay, so this is basically, again, we're using the cell flow cytometry to determine how many cells are insulin producing cells. If you look at in the 3D, you have almost 20% of cells are insulin secreting cells, and 2D only have 5%. That's again indicating the increase. We also I'll skip this one, and we did a glucose challenge. It will see the 3D form the cell clusters and form the much high level of their insulin upon a glucose challenge. And I show you some, this is basically we start using the cell decellularized ECM. We prepare this decellularized ECM from the POC, and then use this decellularized ECM to fabricate the scaffold and for cell differentiation. Again, we detected the cell gene markers to confirm the generated of the beta cells from human ear cells. And I want to skip this one. I don't think I have too much time to talk about this. And I think it's just go to the end, take your questions. And this is the basic, I want to just talk about it very briefly. And so this is basically we recently work on is to try to create a consortium, national consortium, to work on generate the cell technology, allow us to standardize and modularize, produce, and the cell therapies. So this is one very good example, to show this is a slide which I used to summarize how many cell and the products on the market. There's so many different type of products in the market. However, one big problem is how are you going to manufacture, produce the cells? And you will see a lot of report in the CNN, also see a lot of successful clinical try, but those cell products are not really market. The key is the technology, the manufacturing. So we want to form the consortium is to develop technology and allow us to scalable produce those the cell products. Basically, the idea we focus is the scale up and use the biofoundry concept to do the scalable production and also scale out. The scale out is more deal with the small quantity, high volume. In other words, more dealing with the personalized medicine. So scale up is more deals with the massive production of the cells. And I think I skipped those ones. Go to the last slide and technology. And this is basically the people and the contributor researchers present. And this is the funding we received from the agency, the NIH and NSF, and also the private foundations. Thank you. I'm going to take, I think it's maybe one question. Okay. All right.
You said you need a bioreactor as big as football field for one patient. Yeah. With this technology, if you were going to take care of all the people and bring them how much physical space?
Well, that's the problem, and we try to solve. Remember, I mentioned about by later we form the consortiums. Yes, this is based on the current technology. If we want to really bring these treatments into the practice, so we need lots of the build a very gigantic bioreactors. Now we basically the way which we do basically try to convert is a 2D and the 3D. If we convert in the 2D and the 3D, then you don't have to build this kind of football size of bioreactors. You can use the conventional bioreactors, can produce the high very large quantity of the therapeutic cells for treatments. That's basic technology we are developing. So we're working with the large number of the company, and also the large number of the academic universities and across the 5 states, and to form the consortium to develop these technologies. This is a very good question. You probably know is right now CAR T cell treatment is very popular, particularly when our VP announced called the cancer moonshot, and he particularly point to the CAR T cell. So CAR T cell is the treatment is you take the T cell from the patients and introduce the chimeric the cancer antigens into the cells, then sort of the training the cells. Now these T cells and these cells express those specifically cancer antigens, then you can transplant those trained T cell into the patients. Then their immune systems start to fight against the tumor cell, they eliminate tumor cells from the body. So this is basically very successful for individual patients, which you're talking about personalized medicines. However, if you try to use these trained T cells to other patients, if their immune system does not match, and you will not do that. In other words, you have to treat it based on 1-by-1 base, and the treatment is significantly high. Probably at this moment right now, FDA did a calculation, it will cost about $500,000 for this one treatment, one dose. And one dose, there's no guarantee it will work. You're probably talking about the several $1 million and based on the current technology. So now if we will be able to generate the universal T cells and can be transplant to the many patient, we just do the one treatment, one training, and then can be shipped to the every hospitals, then allow people to treat a large number of the patients. And that's basically the technology we are developing. So we're developing the 2 technology, and one is to deal with the patient specific, and second is to deal with this called a universal and the cell products, and can be used for large number of the patient. You can stock those cell products. When you need it, you can store it, and you can directly ship to the hospital and then use to apply to the bedside. So that's basically the key technology for the cell therapeutic manufacturing. So I have to push this technology since 2012. when I was a student on, I served on the subcommittee of the National Science Technology Council. So I proposed this concept. I organized the two study, and one is the group assessment for stem cell science engineering. The other study called a group assessment for advanced biomanufacturing. And that's the recommendation we made to the federal governments and for all the funding agency. And if we want to bring the regenerative medicine into the practice, so we need to figure out a way, we need to create a technology and to allow us to be able to massive produce those universal cell therapeutic products. And also at the same time, we'll be able to produce this patient-specific therapeutic product to deal with some special cases for particularly patient-tailored treatment. All right. I guess I will stay here for quite a while. If you have questions, we can talk about, still later on.
So we're a little bit ahead of schedule. So what we're going to have our second talk, and then we're going to have a longer networking break, hopefully. And then we're going to hear from the 76 West. Brian Bauer just left the room, but he'll be back in. And then we have our team participants. We're going to hear a short elevator pitch from them. So as Bhagat said, for Kaiming, Stan has also a super impressive resume. I'm not going to go through that. You have that in your program. Just want to mention one slight little detail, though, that we're sort of proud of here at Binghamton, which is that he last year was proposed as a candidate for the Nobel Prize by Thomson Reuters. So, of course, he didn't win, unfortunately, last year, but maybe this year. We never know. We never know, Stan. So we're still hoping. So without further ado, if you're a 76 participant, most of you visited his lab today, so you got a great tour. If you're not, I'm sure he's willing to show you his lab anytime. He's also have a co-speaker from BAE, but I'm going to let him introduce the co-speaker himself. And you ready to go, Stan? Almost. So there we go, Professor Stan Whittingham.
Okay, I'll have to juggle three things in my hand then. So what I want to do today is really give a little bit of background about batteries. I know some of you are experts, so my apologies to the experts. I'm going to step back and describe a little bit about what they are and how they can be used. I'm doing the basics. Then Art Lyons from BAE is going to really talk about some of the applications. Particularly exciting because it comes out of the southern tier, and I'm told BAE Systems is the largest provider of lithium batteries themselves in New York State at the moment. Okay? And a lot of those go overseas. So this is my team. Okay? We're the Northeast Center for Chemical Energy Storage. We stretch from San Diego in the west, and you see down here to Cambridge in the UK. So Binghamton's still in the middle. So this is what happens when you have a lot of faculty, and the faculty tend to move. We have no control over that. We're funded through this Energy Frontier Research Center, which is part of basic energy sciences of Department of Energy. There's think about 24, 25 of these Energy Frontier Research Centers throughout the United States. New York, fortunately, has more than their share, but we don't tell DOE that in case they cut us back. So a little bit of history here. For those who don't know about batteries, the first battery was built about 1790, 1800 by Galvani first. He came up with some ideas about frogs and things, and he claimed that frogs had energy. Volta came along and said, no, 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 it's the metallic scalpels you were using that had the energy, not the frog. And he published that in 1800, and I'd like to point out, nothing's changed since then. There are places where you go to present your work and not other places. So Volta went off to London and presented his work at the Royal Society meeting, and it was published in French. French was then the language of science. If you go to his temple on Lake Como, you'll see some of the original batteries there still. About 60 years later, the lead acid battery, all of you are familiar with that, came about, so it's been around a long, long time. And then you had the old manganese oxide cell, and it took about a century before Eveready made what we now know as the standard dry cell you buy in the drugstore. Okay. NiCad is over 100 years old. Hopefully it's been outlawed in almost every application in the US. Certainly Europe's killed it because of the toxicity of the cadmium. And it was in '72 that Exxon decided we needed electric vehicles. And in that time, Exxon decided they were going to be the energy company, not the petroleum company. So they set up a group to look at all different forms of energy. They had a large fuel cell effort. They were the largest manufacturers of solar photovoltaic cells for a long time. They did all the nuclear reprocessing for the United States before the government stopped doing that. So the fairly large operation, and I show you this one out the way. And this is the company, part of Exxon, that did all this, a little company called Exxon Enterprises. They made word processors. They had a very financially successful chip operation for computers. And I think somebody may have written a history about that operation. But they were very active in all these areas from about 1970 to about 1985. And then it dawned on them, these markets aren't very big. In other words, they weren't over $100 million a year, so they basically sold all the technology, but they made a number of breakthroughs before that, and I'll go through a few of them. This here is one of the batteries Exxon made for electric vehicle show in Chicago in '77. This battery is about 6 inches by 4 inches by 1 inch. Used pure lithium inside it. It's probably one of the larger lithium batteries, rechargeable ones till about 4 or 5 years ago. And the industry, if you look at it now, and maybe Art will say a little bit about them, the industry went totally over to cylindrical cells, and now they're swinging back to these what we call prismatic type cells, pouch cells. On the right-hand side, this was a marketing gadget Exxon gave away. It has a lithium battery here, a clock here, and a little solar cell. And they gave away hundreds of these. This one still sits on my desk today. It still works. So you make a good lithium battery, they last forever. And that's one reason all your heart pacemakers, if any of you have them, they're all lithium batteries. They can last for a very long time. So let me briefly explain how these work. It's extremely simple science. When fully charged, you store lithium on this side, and when it's discharged, all lithium moves to this side. It's stored within another solid material in both cases. So a real lithium battery has no pure lithium in it at all. Okay, and I'll show you a picture in a moment why not. So today, this is basically graphite. Lithium's in here. Exxon started with titanium disulfide. This is now mostly cobalt oxide or a mixture of cobalt oxide and other metals. And the lithium just shuttles from one side to the other. This side over to this side and back again on charging. Very simple technology. It has not changed since '72 until today. The principles are still the same. So what's happened to lithium batteries over that period? So in the '70s, Exxon built these cells. You'll see in a moment, none of these batteries, or very few of them, have actual lithium in. Exxon used the lithium aluminum alloy to make it safe. About 10 years later, Moly Energy out of British Columbia started making molybdenum disulfide cells, and these work very well. There's a large deposits of MOS2 in British Columbia. So they were just digging it up and putting it into the batteries. The problem is they were using pure lithium. They had a few problems. These were used in the black boxes of some planes, and they almost brought down 3 planes. So then they took them all out. And since that time, there are no really lithium batteries, rechargeable ones, built in the US using pure lithium anodes. Okay. In 91, John Goodenough had discovered cobalt oxides, exactly the same structure as these two. And Sony had put 10 plus years into lithium batteries, developing them. And I know you're all based in this country. The frustration is no US company, no European company is willing to invest for 10 to 15 years to develop the technology, and that's what you have to do. And basically, Sony was vertically integrated. They had products they wanted lithium batteries for. They made the lithium batteries for those products. About another 10 years later, again, John Goodenough came up with the lithium iron phosphate cathode. That's a very safe cathode, and it's been used in a number of systems, including buses, the grid, and so on. So let me just quickly say where we are now, down the bottom here, where we're going, and the key plot is over here, because there's a lot of industrial folks here. The red line is how the energy density has gone up over the years, from essentially 0, it's about 250. This is on a per cell basis, so it's real data, not lab data. But the key thing here is the blue line. So here, about 10 years ago, lithium batteries were costing about $3,000 a kilowatt hour. Today, it's told GM is willing to pay LG $180 a kilowatt hour. It's been more than the order of magnitude drop in the cost of lithium batteries over that 10-year period. This is partly why almost every other storage technology is not competitive anymore. I'm sure it's partly the reason why GE in the end got out of their sodium batteries. So what's the issue? This is a big table. Don't worry too much about what's in it. This is the chemistry on the left-hand side. Here's a column of the theoretical energy stored per liter. This is the actual. And you can see the percentage here. They vary from about 11% to 19%. So very small fraction of what you should be able to store. Sony just announced a new battery, which should be out in a month or two, where they put a bit of silicon in, and you can see they're now up to almost 25%. We should be able to get that number up to 40%. And that's probably the upper limit. So if some of you are looking for batteries for your devices, whether it's health, cars, whatever, you can anticipate that the actual values here, you should be able to get this up to maybe 1,000 to 1,200. And that's going to be the absolute limit. Okay. Similarly, over this side, oops, let's go. On this side, about 264 now. This may get to 350, 400. And that again will be the limit for lithium batteries. The issue here is mostly the carbon anode I mentioned. That takes up half the volume in the battery, so you have to get that out. Lithium iron phosphate, you can see the numbers there. They're only about 292 versus 570, so it's far too low. So you have to change that out. And the layered oxides, you're only using about 0.6 of the lithium, so a lot left wasted there. If you want to see where the field has been, where it's going, and some of these numbers, look at this IEEE proceedings volume. It's totally open access, this particular centennial volumes, and it discusses every device, every system that's of interest to electrical engineers. So what we're interested in is really to get higher energy density devices, double what we have today, whilst maintaining the power capability. And normally it's very difficult to increase both the energy and the power at the same time. And maintaining the safety. We can't get more energy if it becomes less safe. And obviously everybody wants it cheaper. So this is the issue with lithium anode. this little guy on the right-hand side here, known as a dendrite. Okay. When you charge lithium battery, it could be zinc or anything else, they form dendrites on charging, and these things will grow through anything. So in the battery, you'll have a polymeric separator here. If you put a ceramic one in here, it doesn't really make any difference. Those dendrites grow along the grain boundary. So if these grow, they short the cell out, and this is what happens. And these were some cells AT&T bought from Avastor in Canada, maybe 15 years ago, and about 5 or 6 of them burnt up within a few weeks of each other. So they stopped them. Avastor went bankrupt. And as far as I know, there are no lithium rechargeable batteries sold in the United States which have pure lithium as the anode anymore. So what people are doing is trying to replace the lithium either with silicon or tin. You can react 4 lithiums with silicon or tin. You can react them with aluminum. There's a whole host of materials that lithium reacts with at room temperature. So we've been looking at one of those options, and the one we've been looking at is a tin iron carbon composite. And you can see some of the data here, that the black dots here, this is carbon, the standard graphite anode. It's about 0.8 amperes per cc. This tin iron one is over double it. And that's what we've been targeting, trying to double the volumetric capacity. And I should point out, pure lithium is only about double the capacity of carbon, because lithium takes up a lot of space. Okay. For those of you who are interested, this thing here, C rate, you'll see that on batteries, cells. 1C means you can discharge it, charge it in 1 hour. 10C, 6 minutes, and so on. So that's just a measure of how fast you can get the energy out of those systems. The other area, obviously, you're interested in is the other electrode, which is cobalt oxide. And I show you, this is a typical layered system. This could be titanium disulfide, cobalt oxide, nickel oxide, or whatever. Typically with this formula, 1 lithium, then it has a mixture of these metals. And you'll see different names used, NCA, NCM, that just describes which of these metals is in there. And obviously some differences in safety issues. This structural material is what's used in all your electronics today. It's what's used in the Tesla, the BMW, the GM Volt, and I think we're going to hear it's going to be used probably in the BAE buses in the not too distant future. Okay. So how do we close this gap? How do we get more energy in? One way is to put more nickel into it, and you'll see in a moment why that works. Another way is to get more of the lithium out. Both of these mean you can be charging to a higher voltage, which means you're going to have electrolyte decomposition problems. So there's no free cake here. If you want more energy, it's going to be less safe. And I think the next plot shows this up. Don't worry too much about the details, except if you look at this one on the left-hand side here, this material decomposes at 225. This has the most nickel in it. The one with the least nickel in decomposes at 306. This is what will be in the field called NMC, nickel, manganese, cobalt. This one is what's called NCA. It's nickel, cobalt, aluminum. So you can see there's over 100 degrees difference in the stability of these materials. Why does that concern you? Well, here's the thermal stability plot. This is the capacity. You want to get as much capacity out as you like, but you can see this is the least thermally stable. So you really want to be up here, and this is what our research is targeted at. Get high thermal stability and high capacity at the same time. As the capacity goes up, the capacity retention also goes down. So you want to keep the capacity up there for thousands of cycles so you can give a warranty of 10 years, whatever you want on your battery. So that's one way, put more nickel in. Another way is what Argonne National Lab is doing, and that's put extra manganese and extra lithium in there. So you can see this upper plot here. You can see they're getting about 300 amperes per kilogram in this material. The regular NMC, which is roughly 1/3, 1/3, 1/3, is about 200. But you see exactly the same problem. This nice one here is stable to over 300. These are stable to just over 200. So there's some real stability issues. And it turns out, I'm not sure it's all that public, but basically I think this material is dead at the moment. They licensed it to BASF, and I think BASF has dropped the technology because they cannot get it to work. Okay. The last material I want to talk about is olivine. I said this is, as a cathode, a very safe material. It does not release any oxygen. You can charge it, it won't react with the electrolyte, extremely stable. As I showed you earlier, it has the lowest capacity per unit volume or weight of all the systems. So what we're trying to do is put more than one lithium into related materials. So we're looking at multi-electron systems, basically 2 lithiums in there. And the reason for looking at variations of this is lithium iron phosphate. This is 100% capacity. You cycle it. This shows just 50 cycles. If we did 2,000, it's the same. It's absolutely stable. It doesn't lose any capacity on cycling. Okay. This material is what's used by today by BAE in their buses. It's used by AES in the grid storage system, including the one that used to be across the river here, lithium iron phosphate in it. And it's also the favorite of the Chinese for their e-bikes, taxis, and buses. So it's a very flexible system. It's an interesting system. And I think the thrust in China is because there's no IP issues in China for this particular material. Unlike the other one, which is layered, you'll see this one now has tunnels in it, and the lithium reside in tunnels. It means this one's a little more difficult to make because you have to make sure those tunnels are completely empty. And there's a tendency for the iron here, which should be in here, to go here if you don't make it right. So you have to be very careful to make it. And it's no different than crossing the 201 bridge or any other street in town. If a car breaks down, there's no transport, okay? Similarly here, if you get a blockage in this tunnel, all these lithium ions are no longer available. So you really need to make the material very pure. So we've been looking at a variant on it, and what we did, we got some theorists. These are theorists who were at MIT then, and now at Berkeley, led by Gerd Seeder, and they did calculations of every phosphate couple, every metal you could make with phosphate, what voltage you could expect, what capacity you could expect, and they calculate those. And this is the plot they came up with, and you'll just point out a few lines on here. The red line here is about 4.5 volts. Basically, anything above here is not stable with today's electrolytes, so it would fall apart, so you can't go there. The target area, or DOE and others want electric vehicles, is somewhere between 600 and 800. This is lithium iron phosphate. It's too low. You really want to be over here. And basically on the phosphates, there's nothing over there. So the game we played, we kind of looked at, well, we got molybdenum here. We can go from 3+ to 6+. If we add these 3 together, we get over here. That didn't work out. We looked at vanadium, 3+ going to 5+. So if you add these 2 together, you get somewhere over here. So most of our effort's been on vanadium materials and pushing them, and there's some data on the next slide. And this basically shows you how did we look at this particular compound. This again is a tunnel structure, so very stable, and we thought in this tunnel structure the ions would go in all 3 dimensions. Our theorists tell us it's probably not the case, but we're still looking at that. We looked at this compound because this hydrogen analog of it is used as an oxidation catalyst in the petroleum industry. It's easy to get hold of. So we just built a lithium battery with this in it, charged it, and you can see here's the charging voltage. We can get current out of it, and what we can do in reality is just pull out all those hydrogens. You charge it out, come the hydrogens, then on discharge, we can put lithium back in. And this is just one lithium going back in. And if we keep going to a lower voltage, we get a second lithium back in. So we said, this is a good compound. It should work. Let's study it a bit more. So we have a lot of effort looking at this material. It comes in 7 different crystal structures. So for scientists funding by the basic part of DOE, this is ideal. It means we've got to find out which is best and why it's best. And so we're very interested in how do you synthesize this different phases. The thermodynamics, which tells us how much energy we can store. We're very interested in how stable it is. What's it going to react with? And also we're interested in the kinetics of reaction, which gives us the power we can get out of such a system. So here's some of the data we got here. You can now see the capacity of this one's about 240, 250. Remember, lithium iron phosphate was about 170. The layered oxides were about 180. Those high energy ones were about 250. So we're getting very good capacity out of this. The challenge in all these, we're going over 2 oxidation states, vanadium 5,4, then 4,3. So we got a 1 voltage plateau here and another one down here. So we have to be able to handle those in a real environment, and it's easily doable. It's only a matter of dollars. The bigger that voltage gap up, the bigger the issue with DC-DC converters. Okay. So we can cycle this quite well. Our theorists did all the calculations, and you can see these are the voltages they calculate, almost perfect fit with the experimental ones. So what we're really looking at, we're looking at other phases, and then now calculating the voltages of the other phases before we measure it. So we'll see how good they are when they don't know the answer. So let me just finish off this bit of the presentation by saying what we do here in this building under the center is fundamental research. We're trying to understand why things work, what are the inherent limitations, and how can we push those limitations. So we work with a mixture of chemists, physicists, material scientists, engineers, a few organic chemists. So we have mixed interdisciplinary groups here, just as you would in an industrial organization. So we kind of cross the academic boundaries. DOE obviously wants transformational research and only research that teams can accomplish. So one of the messages they tell us, Stan, if we gave you all the money you wanted, all the time you wanted, could you do it? And if the answer is yes, we're not going to fund you. Okay. They want us where we say we've got to have Gerd Cedar out at Berkeley or Shirley Meng down in San Diego and Claire Gray in Cambridge. They are critical parts of the program, and without them, we couldn't do it. So I described these 2 parts. The other funding we have here is from the applied side of DOE. And here we're working on what they call beyond lithium ion. This is where we're trying to replace the carbon. And what I didn't talk about today is actually working on reactions that are not these intercalation reactions. In the present batteries, you retain the crystal structure. In these systems, you intentionally destroy the crystal structure. So in this case, if you're working with copper fluoride, you're going to make copper metal and lithium fluoride. You can get a much higher capacity. The voltage is somewhat lower, and there's real issues with power capabilities. But these are maybe some of the systems of the future. What we have here in Binghamton may be of interest to some of you. We have right now, we've placed an order for a dry room to go in this building. So we actually be able to make lithium batteries in this building and hopefully have reproducible systems winter and summer. We can make very good batteries here in the winter. As soon as the humidity gets up, you have problems. And I think that's universal. Some of you know we have advanced characterization capabilities, right? In the adjoining building, $20 million of characterization, which is available basically to anybody in the state, and it's fairly reasonable prices. We do a lot of work in our center at the various national labs. So the way we do that, the easy way, we actually embed either a postdoc or a graduate student at the national lab. So we have one at Berkeley right now, we have one at Brookhaven, and one will start at Argonne in the next few months. So we can have access to all their facilities. And these are critical for a number of these systems. If you have a battery that fails, if you pull it apart and look at it, it tells you one thing. You really want to look at it whilst it's operating, because what you get out of an operating system is very, very different than what you get out of a system that's being allowed to equilibrate. And the other area where we're very actively involved is the New York Battery Energy Storage Technology Consortium. This is now maybe 8, 10 years old. I'm vice chair of the board of directors of it. Mike Field up at the forklift company up the road, he's chairman of the board. So this is, in a sense, a bit of Binghamton-oriented activity, but it brings together industry, academia, the utilities, the auto companies, the investors all together, so we can have a communal discussions of where we're going and all the rest of it. And at this point, I will hand over to Art Lyons, and maybe we'll hold questions until the end, unless it's something urgent.
Good afternoon. My name is Art Lyons. I've worked for BAE Systems. Professor Whittingham here asked me to just come say a few words on what we do. One of his questions is, how did BAE Systems ever get into hybrid? Our area of expertise has always been defense, a lot of commercial aircraft, aviation. How did we get into a commercial product like this? Well, beginning was 1995, and there was a group of us that had a lot of technology from the aircraft power systems, and we said, this hybrid thing looks kind of cool. There was a lot of EV work in the industry being done, but the battery was a limitation. And we said, if we could augment the battery with a small diesel genset, maybe we can make a hybrid vehicle work. We did just that. We had a Chrysler T-Van. We went and bought a generator from probably a company like Home Depot, threw it in the back, cut a big hole in the back, put an exhaust in it. Wasn't the most pleasant vehicle to ride in, but we learned some of our first things about hybrid vehicles, driving this around the streets of Binghamton. We've got a long heritage in the hybrid world. It really came out of our aircraft control technology. Back in the mid-'80s, we were putting electric actuation systems on aircraft. High voltage DC systems, 350 volt DC systems, trying to replace all the hydraulics. So we had a lot of capability in the power side, coming up with gen sets, taking the power from the engines and distributing it to all the different actuators for movement of those surfaces. We kind of were looking as a defense company, more commercial. We like to do a lot of commercial. We do a lot of commercial aviation. We like to maintain that balance. So we started to take some of that technology and push it into rail and transportation type systems, things that required long life. And eventually we spun that into our first hybrid, which we launched in 1995. Was actually delivered into revenue service for New York City in 1997. We had a fleet of about 10 buses that ran for a couple of years, really learning about the hybrid technology. The market was kind of slow. It really started to take off around the year 2000. In 2005, we revved that system to a newer generation. In 2010, we did a parallel system where we blend the diesel engine power with the electric machine and actually use both mechanical and electrical power to drive the vehicle. And we have a few of those trucks running around with New York City Sanitation Department for some refuse trucks. And then 2015, we have some new generation series products coming out. Of course, we're going to take this technology, and it's kind of like a loop. We'll spin it back into the aircraft technology as well. We played across a whole large fleet of markets. We built a lot of different vehicles over the years. This is our core hybrid drive. It's what we call a series hybrid drive. There's no connection between the engine and the wheels. It's all done electrically. The engine, even though it looks connected, the engine drives a diesel generator. We make a 650 volt DC link off that generator. That DC link then is converted back to the traction machine to make the vehicle move. There's a propulsion control system in the top left. That's basically a dual inverter stage. It's a large vehicle. That's our niche. We're never going to go compete in the small automotive market. This is 200 plus kilowatt system, very large, and has to have a very long life. These vehicles drive for 12 to 18 years. Our customers demand 52,000 hours of operational life, which is very tough for any electronics, not alone a battery. We also provide the accessory power for the vehicle. We put as much power or energy into accessories, keeping the passengers comfortable, running the air conditioning, running the lights, running the heat, as we do into propulsion. It's about a 50-50 balance. And then, of course, the topic is the energy storage system. When we launched this product, we used lead. Lead was our energy storage of choice. Lithium ion wasn't even commercially viable at the time for a vehicle of this size. And we'll talk a little bit more about that. Where are we? We work with 5 large OEMs across the globe, a couple in Italy, Iveco, one Alexander Dennis. You'll see the double-decker buses that run around London, and then a couple companies, Nova Bus from Canada, and then New Flyer and Gillig. We've got a pretty large fleet. We're up over 5,000 buses, quite a few of them in Europe, quite a few of them in North America. We are the market leader, and we have a fairly significant IP portfolio over the years. 5,000 buses across the globe. That saves about 11 million gallons of fuel, takes about 20,000 cars off the road. It's equivalent to planting 80,000 acres of trees. We've got a new product out where the energy storage is going. Everyone wants more. They want start-stop. In other words, you come up to a bus stop, they want that engine off. They just want you to run on battery mode, nice and quiet, very ergonomic and friendly for depots. A lot of buses, you think about New York City, one particular depot has 300 buses pulling out at 5 a.m. in the morning. They have a huge noise issue. They want them all to go away at least a mile, nice and quiet. So they want to use the battery. And then silent drive. A lot of cities like London has certain centers in the city where they want totally zero emissions vehicle capability. So you may go in on hybrid mode, diesel generator. You'll end up shutting off, run electric mode for maybe 5 kilometers. And then once you're out of that city center, you can, again, resume the hybrid operation. So again, more demands on the battery. I'm not going to spend too much time on these slides, but we really got into this because we had a lot of core competencies. And one of our competencies was high reliability packaging for very harsh environments. We put a lot of controls and computers on products that have to last a long time in very harsh environments, bolted to the side of jet engines is one example. We had a lot of capability from electric actuation on rotating machines. We blended that into our hybrid, and we had a lot of capability of basically doing mission profile work, understanding how to take that application or drive cycle and decompose that into the failure modes and mechanisms of the components themselves. And we're really targeted after automotive cost models that require long vehicle life and high reliability. Put in perspective, we're 52,000 hours. Your typical car, the way we drive it, we're lucky if we get 3,000 to 4,000 hours on that car. It's a huge difference. Pretty skilled in the rotating machine design, again, out of the electric aircraft industry. We cover a large gamut. A lot of the machines that are in your Toyota Prius today, the very advanced internal PM type machines, we were doing those in the mid-'80s for aircraft. And that technology has kind of come out of that marketplace and become pretty common in the industry today. And then what we brought to it was a lot of systems integration and control. We worked with a lot of vehicle OEMs, and when we first started this, the vehicle OEM had no clue how to actually do the integration of the overall system. Managing a diesel engine, putting a battery system in there, putting the power electronics in there in the machines. So we really brought a lot of systems integration and control capability from our heritage background. So what do we require from a battery? Few ground rules. There's 2 types of batteries out there. A lot of them are energy. People want a lot of energy. They want that cell phone to last for 5-6 days before you have to recharge it. Unfortunately, the HEV doesn't really need a lot of energy just to drive the bus. We need a lot of power. When you stop a bus that weighs 40,000 pounds, you're looking at a megawatt of braking energy. And I've got 5 seconds to capture that. Okay, so I want to push all that energy, or excuse me, all that power very quickly into that battery. And then if you look at what they want to do in the city centers and start to do more electric vehicle type operation, now they also want a lot of energy because now I've got to drive off that battery for a long time as I get through that 5 kilometers. Obviously, not all the cells are created equal, and there's different ways to do the designs of those cells, how much active material you put versus how much non-active material to balance between energy and power. We can always take energy cells and get power out of them by putting more and more in parallel. If I put more energy cells in parallel, eventually I got a cell that's, or a battery that's capable of making the power, but unfortunately my cost and my size and my weight go way up. So it becomes uneconomical. So this is our current production lithium-ion battery. This was fielded in 2006. It was based off an A123 iron phosphate chemistry. And we really started working with A123 when they were really an MIT spin-off company. That's how early we were in with A123. And we had lead on our bus. The lead batteries themselves weighed 4,000 pounds. And we were able to work with A123 and come up with this solution that weighed 800 pounds and really do the job that we wanted it to do. We're kind of abusive on the battery. If you look at the C rates that we run there, it's 15 C. A lot of batteries don't have a hard time giving you 15 C in a discharge mode. But when you want to stuff that energy back in at 15 C, that's pretty hard on the battery. And I will contend there was no other battery at the time that would even come close to what this little battery can do. Now I say little battery because each one's about the size of a C cell. And we run 1,500 of them in series parallel combination to build this battery pack. But it's still a fairly high dense pack. It does about 11 kilowatt hours of energy. About 10 inches high, about 41 inches wide, about 84 inches long. And that's going to be our space claim as we go forward. So pretty early, we were the first of anyone to field lithium ion in a mobile application. As we go forward, obviously that's pretty old. It's over a decade old since we fielded that. Technologies move forward. Professors like Stan and his group are moving that technology forward. There's a lot of choices for us out there. We're not into developing the chemistry. We're into understanding what the chemistries are, how they work for us, and how they work in our application. But when you go out to the market, they're all marketeers. Everything can do everything, but when you really go test it, you have to understand how you use it in that application. A lot of different choices. As Stan mentioned, form factors are changing. They all went cylindrical. They do seem to be coming back towards pouches and prismatic, which would be the top right, kind of a square can type approach. The square can has an advantage because it gives you the packaging capability with it. It's kind of, they've handled everything. When you do a pouch, you've got to apply the mechanical constraints to that pouch to make it last. A key one for us is sustainability. There's been a lot of battery companies that came. The government put a lot of money into the battery industry. Not all of those guys survived. And even some of them had what I would say is very good technology, but they didn't make it and they weren't sustainable. And for us to pick one of those in a commercial environment would be bad. Cycling. This is what does it in for us for the most part. As we cycle that battery, charge it, discharge it, we want to do that a lot of times during a day. We pick a fairly big battery, so when we charge and discharge, we may be only using 1 or 2% of the capability of that battery, but we're expecting a lot of cycles. If you look at it, and the shallower we cycle, the more cycles we can do. This particular battery that I've plotted here can do about 23,000 cycles if you take it all the way from 100% to 0. But if I only go 2% on those cycles, I now take that number to 1.3 million cycles. Okay, and that's kind of where the HEV uses it. And you look at the power that you push through that battery over the course of its life, it's enough to power your house for 80 years. Okay, and that's what we use in a battery for 6 years on a bus. Why does cycling fail it? There's a lot of electrochemistry here that I'm not going to pretend to broach, but there's more than electrochemistry going on here. As we start to shove those ions into those little matrices on the anode and cathode, mechanical damage can happen. And a lot of the cycling, when we run these C rates and how fast we're shoving those ions across, when they hit that matrix, it kind of damages it. And it's more of a mechanical wear out mechanism. And you can actually mechanically go through some of the structural tools and mimic that loss mechanism for capacity. So after you get through the cycling, well, now I got a battery. I'm not going to cycle it too hard. I understand that. Unfortunately, it still wears out. Even if you put it on the shelf, nice, fully charged, it's going to age. And you need to understand that when you're building a product that's got to last 12 years, because that aging is significant. And it's typically modeled through the electrochemistry by typical equations like the Arrhenius equation. It's activation energy. The hotter the battery runs, the more active that the chemical reactions are. You get more side reactions, and the battery ages. For us, these calendar and cycling wear out. Basically, how do they show up to us? Obviously, decrease in capacity. I can no longer go the 5 kilometers I want to when I'm in EV mode. Or increase in resistance. The resistance continues to grow, and now I can no longer push the power in and out of the battery I want, and that's really critical for your HEV applications. So I like to look at the battery. There's a lot of different mechanisms for both the resistance growth and the capacity loss, but it's really an electrochemical, mechanical system at the end of the day when we look at it. Stan mentioned this a little bit. We're putting a lot of cells in series, a lot of cells in parallel to make a total battery system. We need a management system to go with that. System safety is number one. Lithium-ion batteries, if you overcharge them, depending on their chemistry, don't really behave that well. When we first got into lithium-ion batteries, we had a battery out of a Chinese company that was a lithium cobalt battery. And all anyone would tell us, if you overcharge it, it's going to have rapid disassembly. What does rapid disassembly mean? So being the creative engineers that we were, we're like, we're going to go find out. Well, I scared half the neighborhood when it went off, and it was a cobalt chemistry, and I'll never do it again. But we did it safely, but it was still quite interesting. Now, not all lithium-ion batteries have the same safety issues. Cobalt is one of the ones that's a little more exciting. State of health, a lot of algorithms in to understand as we cycle the battery, as the battery calendar ages. All my customers want to know, how much is my battery? Is it 6 years? Is it going to go another 4 years? They want to understand when they're going to replace it. And then cell balancing. We have a lot of cells in series. You got to balance them. If I get one cell in that series string that's at 0 and the rest are at full, my battery pack is at 0. So how you balance those cells is very critical as well. Safety, we talked about this a little bit. Just put a few exciting pictures in. We go through a lot of safety testing. Every chemistry is different. Some of them you do a nail penetration, some will be an overcharge. They all have their reactions. Most of them will burn at some level. We do all this testing at cell level, take it up to a module level, and then ultimately at the top level, at the pack level. And as Stan mentioned, phosphate is one of the safer chemistries, but there are some other chemistries that have reasonable safety that give us better capability. So we challenged our team. We wanted a new battery pack going forward. Obviously wanted increased performance in every aspect. Obviously nobody wants to pay anything, so we had to lower the cost. Want to drive it harder, make it do more, want it to last longer, and we all want it for free. What we came up with is a modular concept that takes a lot of different modules. Obviously, each module would be custom designed to fit into this envelope. But the battery on the left is a NMC chemistry. I'm not going to name the cell provider at this time. But we were able to take that same space claim that you saw earlier. It hasn't changed. And put 3 times more energy into that same space claim while maintaining the power required for the HEV application. Fairly impressive. Weight is about neutral. But that's kind of where the technology's gone. I will also say that packaging the square form factor cells help, because when you package round cells, there's still a lot of space left that you can't actually use. Heat is always an issue. You got to get the heat out of these batteries, especially in HEV. We generate a lot of heat. So there's a little air conditioning on the front of that system that keep that battery cool. Just like you and I, we like to be at a nice 25 to 30 C. 30 might be a little hot for me, but so the battery likes to be right in that sweet spot. And of course, on the right, there are some customers that really wanted low cost. And in that case, they only wanted the power. We gave them an ultra capacitor system. You can see the energy density of that pack is pretty poor, 0.8 kilowatt hours in the same space. It delivers the power at a lower cost. And it's good for a lot of customers like London, where it's totally flat. They don't have to go up any hills. Okay, while the pack, and they don't want any EV capability potentially. So that would be a pack for them, because I can probably only do about 500 yards of EV capability and it'd be gone. One acceleration. Or the pack on the left, where we can do about 5 to 6 kilometers of EV range to run those city centers. So we've kind of developed, because when we started HEV, we really had no energy storage. We grabbed lead acid batteries. It's kind of what was available to us. The industry said, you're never going to get anywhere with them. Our customers in New York City is still running lead acid to this day on about 2,000 of their buses, and they love them. They have a known replacement schedule. We get about 3 years of life out of them. They're not too expensive to replace. So they're very comfortable with them and have been. So a lot of capability. I think for that, we can take some questions. Yes. The batteries are not a design for disassembly. At a module level, the module is, once it's welded together, they're all pouch cells with tabs. Once that welding process is complete, you're done. It's welded together. There are people on our older battery that actually, that's a resistance weld. There are some of our customers reclaiming those and mixing and matching those. But on the new one, that's going to be a little more difficult. So we've been looking at a lot of different programs, and they're obviously recycled different places. But one of the things we've been looking to do is take some of our batteries and push them back into grid energy storage. The industry says that your batteries are end of life at 80% capacity. Well, if I got a battery that's still at 80%, maybe I can't do what the HEV vehicle needs to do, but I still got a lot of energy left in that battery, and that could run in other markets. Yes. I'm an alumni. We haven't worked together a lot. We have not worked together a lot on these type of projects. Maybe Raj could say a little more on that, but we have a relationship with Binghamton, but not so much on the hybrid. Yes. Yes. Everyone wants to know how to make their cell phone last longer. No, last battery life longer. And you can comment. I'll give you my 2 cents. But one of the things in there, a lot of lithium-ion batteries from a life. Most of that is you're at very slow C rates. You're not pushing it hard. So your aging is going to be more temperature dependent. How hot does it run? And keeping it at 100% state of charge is bad. Okay, because your chemical reactions and everything are much more active up there. Keeping it at 80% down to maybe 40%, that's probably your sweet spot you should try to maintain in it. And it'll last longer there.
I should perhaps add that the phone manufacturers probably control it within that range. So when it says it's empty, it's probably got 30% still left in it. And does anybody today replace their battery in their cell phone? Well, you just buy a new cell phone after 2 years, right? So this is the big challenge, I think. Cell phones, they last okay. The buses and the cars, you want 10-year warranties. this is just one slide for anybody who doesn't realize how the changes have happened in the last century. Okay, the oldest one there is Edison's car with his battery in it. The two beneath it are two cars built by GM and others in the 1970s, the gas crisis, same time Exxon was in it. And you recognize the others, and the two in the right top are both BAE systems. And Art didn't mention, though, they have fuel cell buses which have a large battery in them as well. Right. We didn't know they were going to get like 20 minutes.
I didn't either. I texted him last night, like, can I have an extra 5 minutes? Yes. So the Prius came out with nickel metal hydride, and I will assure you Toyota made them accurate. Because if you actually go look at the Prius, when it came out day one, they give you a lot of performance. But Toyota is taking that performance away slowly as they go. So they controlled it so they would actually hit that end projection life. And they hit it pretty well. Yeah, so I've got a friend that's got 2 old Priuses, and he's actually taken and bought modules and cells and put them in the battery pack, and he's been very successful replacing them and had no issues with the electronics on the Prius doing that. There was a question over here somewhere. Yes. Correct. We have talked about combining. We've had a capacitor. New York City has had a couple of our capacitor buses running for 10 years, and they love them. It's just we built 2 prototypes way back when Maxwell first came out with a couple cells. And since that day, we've been talking about, can we combine capacitors and batteries to come up with something better? And the ultimate answer is you could, but it's not cost effective, because now I end up with both components in the system. It just never works cost-wise for us. We have tried. Yes. We've worked with a couple different companies looking at taking our older batteries and putting them into grid storage. We have some couple active trials ongoing with that right now today. Maybe we can talk. Yes. Harsher in every aspect. We're selling to transit properties that still have to operate, so it's difficult sometimes to, meet their satisfactions, and sometimes they're more demanding on you than the government ever was. The product itself, when we first started, we got this long-lasting product in the defense side. We know what it does. We're going to go play in this commercial world. That product doesn't have to be as robust as what it had to be over there, and it's actually the other way. The life requirements at least in the transit industry, are much greater and much more demanding than they are in a lot of our military applications. Typical military, 3,000 to 4,000 hours, they're going to go rebuild it after that. These guys aren't rebuilding after 3,000 to 4,000 hours. And some of these buses in London, it's amazing. They drive them 24 hours a day, non-stop. They never rest. Yes. We work with a lot of the different cell manufacturers, whether it's in Korea, China, same cells built in the States. So supply manufacture really hasn't been a problem. The A123 cells today that we buy, they're built in China, and their quality has been very good. Have no issues with that. Where we struggle more is losing my train of thought. Just ask the last part of the question again. Just no, we're global. It has not been an issue. I mean, in North America, there's by North America compliance we have to maintain, so that companies get their federal subsidies and funding. So sometimes we have to produce a lot of that in North America. Today we buy those cells in China. We're packaging them here. We can meet those type of numbers. My wish list is more standards around batteries. You saw the different form factors. They're all over the map. And every time, somebody builds a new pouch cell, the dimensions are all different. There is no standard battery size today. And that's really difficult because you don't want to lock yourself into just one guy and his size. And that's why we tried to come up with a strategy at the top level to make it modular. So we don't have to redesign everything, but we can take a new module and potentially drop it in. It's not guaranteed, but we've tried. We have, the whole market dynamically right now is moving towards EV. That's where everybody thinks they're going to want to be. We have several vehicles that are plug-in hybrid today. The quantities are small still. We have full capabilities of EV, where they are doing very fast charge, so there's no engine anymore. And we have battery systems on those that they're just rapidly charging, whether it's en route, overhead catenary, or a fast plug-in charger. A lot of those programs are happening more on the European side. We do have a couple EVs running over in California. And as Stan said, we do have a lot of fuel cell work. We've probably got 20 fuel cell buses out there that are operating as well. Problem with the EV market, as I see it, there's still a huge infrastructure challenge. One of our customers up in King County, out in Seattle, they've got 5 EV buses. That's all they can handle because they don't have the infrastructure to put any more than 5 in. And when you start to go into put infrastructure into a city, that's major cost, major rework, and it gets very difficult for places like New York or large cities to put that infrastructure in. I'm probably not the right guy. I could say maybe a little bit. It's challenging. It's expensive. We're pretty successful with capturing a good market share of what's out there in fuel cells. It's still determined whether it's really going to go forward. We carry onboard hydrogen, so we're not. When we first started, we built our first fuel cell in 1998, and that was with the University of Georgetown. And on that one, we actually put what I call a chemical refinery on the back of the plant to take methanol and turn it into hydrogen. But today we put hydrogen on board in compressed tanks. There are cities that really like it for the zero emissions, but I don't see it going long term in the marketplace today. There's just too many barriers to put in the hydrogen refueling stations again. So it's kind of a niche application. Yes. So it's a similar technology, but in that one on the Bates Troy truck, it was we developed a system for what I'd call the city pickup and delivery truck market. And in that system, we wanted to get cost out. So we went to a parallel system, kind of like the Prius, where we blend power mechanically through the engine to the drivetrain, and then we're augmenting that power with a single electric machine and a battery system and an inverter. So it's about half of the components that a series hybrid system would take. That's what's in the Bates Troy truck. And we've got 3 of those in New York City running in refuse trucks as well. And they're looking to purchase more. It's a product we took to about 90% completion to the market. But with the price of fuel going down, there was us and a few other competitors that had markets. Our largest competitor, Allison Transmission, also built a parallel system, but they're all installed because that market's very private, very competitive, and every dollar counts to them. So unless it's subsidized a little bit, it's just not going anywhere. And if the price of fuel was to go back up, there'd be a shot. But when it's sitting down here at $3 a gallon for diesel, it'll never pay back. So the operators are like, we can't afford it. Yes. I'll take that one to you.
It's politics. Talk to your politicians. Every motor-driven vehicle in New York State has to be registered, and they haven't worked out a way to register e-bikes, all these things you stand on and run around, hoverboards. None of those are. Yeah, but other states do allow it. New York, for some reason, does not. So it's a political issue, and
All right, very good. Let's give a final round of applause. And we are now break, Laura, or? 3:45, so we'll be back in 3:45, and then we have 76 West. Thank you.
Yours is up next, but the other one's both in first, and yours is not normalized. I'll still start with it.
What I'll do is stand over here, and then I'll roughly let the person, we'll have a group there, and when the person comes up, they can step forward, stand in the middle. And we'll have 2 mics. Do my best.
I'm just here to apply.
I can do one piece of
No idea. It's hard to see. I'm just gonna have them all come up here. And then the 30 seconds. What I thought we'd do is get them all to come up and stand over here at once, because 30 seconds isn't very long.
Yes.
That way it's not back and
That way they can
forth
just
and
kinda
back and forth.
Hang around here and then,
Yeah.
well, it's only gonna be one person pitching, so it's only 12 people. Yeah, 13.
I'm signed up for an elevator pitch, I
Yes,
think.
you
Yes,
are.
you are. You're 1, 2, 3, fourth one.
Fourth one,
And
okay.
We're gonna have you all come up and kind of stand over here so we can do kind of clickety click.
Okay,
click.
all right.
And I'm gonna speak for about 5 minutes.
Okay,
We'll call you.
We'll call you down. I'll call you down my group.
Yeah, he's gonna have a seat.
so when is that gonna start? 10 minutes, okay.
Actually, it's supposed to start now,
Let's go. Yep.
but I think there's still people straggling yet.
It's gonna go use the restroom.
Probably have time for that.
Probably do.
You have time for that? Well, I can sit up there while you're. Sure.
Okay. We'll get started again. So I found it fascinating to see the presenters this afternoon. Some amazing things going on business-wise, technology-wise here in Binghamton. I'm here, I'm Brian Bauer. I am the program director for 76 West. I work for the Southern Tier Startup Alliance. For those who don't know what that is, the Southern Tier Startup Alliance is an effort on behalf of Binghamton University, Cornell, and Corning Inc. We work together to promote entrepreneurship in the Southern Tier. We are an organization, a membership group of business incubators across the region, currently representing six and growing incubators. So here in town, we have the Startup Suites just around us in this building here. We also have the center down in Binghamton. There's a couple of incubators in Ithaca and a couple of incubators in Corning and West today. And of course, a big new building being built and opening here in 2017. So tremendous things going on in entrepreneurship in the Southern Tier. A little over a year ago, Governor Cuomo announced 76 West. I'm going to talk a little bit about that program, and I'm really excited to say to you today that we have the 24 semifinal teams in the region this week preparing to compete to win $2.5 million in prize money this year. So I'm going to talk to you a little bit about that. We're actually going to call them up. Some of the teams are here and are able to come up and do a 30-second intro to their company. I say 30 seconds, slightly tongue-in-cheek, but a brief intro. we don't want them to give away their thunder for their big competitive pitches tomorrow. So we'll try to keep them. If you see me like elbowing them or throttling them, pulling them off the stage, that's what I'm trying to do, is keep them under control. Actually, Tony will be helping me with that. So before I got going with this, I wanted to acknowledge an aspect of the program. We work with a great group of mentors, people that are assigned to those businesses to help them, and they've been helping them this week on their pitches. And so those mentors that are here, and there's a few in the room, if you just put up your hand, that would be great. I know Tony's here. We've got Aaron and Felix, Jason, Brad, Don, Ed, back in the corner, Ken, Clayton. So these are all people, if you haven't met them, some of them are like Tony, are from here and you see them a lot. Some of them not so much. They're here and they're great resources for the entrepreneurial community. I was also really pleased to see BAE Systems speaking about the hybrid drive bus and the work they're doing. Really thrilled to see the work in battery technology. A couple of us were down on a tour of Stan Whittingham's battery lab, and they couldn't really drag us out of there. It was awesome. Where's Joshua? Is he here? He's not here right now, but we had a great tour. So thank you for that, Stan's lab. So let me say a few words about 76 West. It's a clean energy business competition. Why is it called 76 West? If you don't know and you think you figured it out on your own, any guesses? Jason. It's the longitude running roughly here through Vestal. Now, it's a kind of a goofy name for the southern tier, which kind of runs east-west, and it's a longitudinal line running north-south. But it was a play, really, on 43 North, which is a big business competition in Buffalo. And 76 West was also born out of, I think, the governor's office's idea to generate economic activity, and that's the competition. I like the name because it requires me to then explain, what is that? What is a clean energy business competition? There's a $20 million budget, $10 million in prizes, $10 million in support over the next 4 years to build a clean energy ecosystem in the southern tier. When this first came up, I've got to be honest, I'm business competition, I get it, I like that, but I'm like, how is that really going to make things different? What I love about 76 West, and what I think does make a huge difference, is it's built around the concept of how you integrate those businesses into the region, how you introduce them to businesses like BAE, or technologists and technologies like Stan Whittingham's lab. And so we've been this week in Corning on Tuesday, talking about what's happening at Corning Inc. and in Corning in the area and west to Fredonia. And we've been in Ithaca yesterday, met a lot of the facilities and people and businesses there. And then we're down here in Binghamton doing the same. It's a very quick whirlwind tour for the businesses that have come this far. So it's been great. We also, so like I said, in addition to prize money, it says 10 million. That's 10 million over 4 years. That's $2.5 million a year for 4 years. Top prize, $1 million. So it's a big deal. 10 million in support too. So the businesses will get incubator space. So they'll get access to the incubators here in Binghamton or in Corning or up in Ithaca or out in Fredonia, Alfred, as they choose. The competition is open nationally, open internationally, and open to folks here in the state. It's also for startups. Well, what is a startup? This is for early stage companies. Does mean that you've got to be a company. You have to be established. You can be early revenue, pre-revenue, got to be roughly less than 7 years old. The idea, though, and the easiest way I describe what's the right stage of development is, do you make the best pitch for $1 million? And so these teams tomorrow, 24 teams up on in Ithaca on Cornell's campus will be pitching. Here's what I'll do with $1 million, $500,000, $250,000. What's clean energy? Well, I'd like to delineate clean energy from clean tech. They're related, they overlap. Clean energy is focused on energy generation, energy efficiency, and reducing the climate impact of the existing energy systems, so things like carbon sequestration. And so there are some businesses that don't immediately leap out, that don't seem like a solar business or an obvious clean energy business, but they are working in their space to be revolutionary in energy efficiency, which is equally compelling.
So it's $1 million grand prize, $500,000 second prize, and $250,000 prizes. What will happen tomorrow? 24 teams will pitch. We've got 2 panels of judges. They will recommend to the state at the end of the day 6 finalists. Within a few weeks, the state will announce who those 6 finalists are, and then we'll have a month or a month and a half to work with those teams to prepare them for a major pitch competition here in Binghamton in mid-July sometime. Dates to be finalized and announced soon. But we do know the finals will be here in Binghamton. I've mentioned some of the mentors who've worked hard with the teams the past couple of days. Talked about connections, introductions to people here at Binghamton in the university or in business. All these things are what we're trying to offer the companies. One aspect of the competition is about creating business here in the Southern Tier. We contemplated, does that mean, in 43 North, that means you need to move your business to Buffalo, which I get that choice. Didn't seem so obvious how we would do that here in the Southern Tier. A lot of the companies that are interested are from elsewhere in New York State. So instead of using state money to pull companies across county lines into the Southern Tier, we've said, no, you can pitch how you'll get involved here with partners, customers, suppliers, facilities, technologies, other ways. And so it's an interesting aspect of the program. It does make us kind of a regional-minded program. So in addition to Cornell, Binghamton, Corning working together, we've partnered with other organizations from around the state who have been fabulous in helping us pull this together. I would highlight Mike Riedlinger, if you're, thank you, Mike is right there. He's with High Tech Rochester. He helped deliver the training. They run Nexus New York, another NYSERDA program, and they have been a huge partner along with several other organizations. I'm also really remiss, I can't believe I forgot this, I must be getting tired. NYSERDA, this is a NYSERDA program, and my guy, my man, is right here in the middle, Mike Shimazu. You got to stand up, Mike. Come on, come on. Stand up, Mike. So it's a, I wondered who kept kicking me. I'm like, what am I forgetting? So it is a NYSERDA program. We all work for Mike. He wants to run a great program for the governor's office for NYSERDA. And NYSERDA does a lot of great things. Several of us mentors met each other at the Nexus New York program that High Tech Rochester runs. And so it's great to see those things coming to fruition. A lot of these companies, at least a fraction of them, have been through that program in one way, shape, or form. There's a lot of other good programs around the state, but I'll call out that one in particular. So this is the inaugural year. Quick calendar. We accepted applications through March 15th. We're having the semifinals now. The finals will be in July. We've had a bunch of events across the region. This map is convenient because it gets you an idea what is the Southern Tier. Normally it ends right there. 3 counties, 4th county in would be Steuben. The 3 counties to the west were added. So in 76 West speak, it's 11 counties all the way out to Chautauqua, Allegheny, and Cattaraugus out to the west. So who are the semifinalists? And at this point, we're going to start, those of you who are able to give a 30-second pitch would mind making your way down to roughly where I'm standing, I'd appreciate it. We have 24 companies. Some of these names are local favorites. They range all over the place. You have Chroma Nanotech here based out of the startup suites. LC Drives, what the heck? Something happened to LC Drives and they got turned sideways. Well, no, it's a special twist on LC Drives. But a few I'd highlight. Uma Bioseed is highlighted here. How is that clean energy? They are a technology that improves agricultural efficiencies in energy, for example. I won't make their pitch for them, but that's essentially it. A couple more companies. Heights, I think, is also based here nearby. Applied Biorefinery Sciences out of Syracuse, working on some stuff down in Alfred University. Many other companies. So ranging all over the place, from battery technology to things that you're going to hear about here in a moment. So one more set. So these are the 24 companies, and I'd just like to give them a round of applause because many of them are here. These 24 companies have all risen above, if you will, a huge pool of applicants. There were many, many fine companies that didn't make the semifinals. that could easily have been here. I can honestly say that any one of these companies, I'd be proud to have them be a finalist. The judges have a tough job to do tomorrow. And so, Tony Frontera, please come down. Tony is going to help me out because my brain is flagging and I need, so he's gonna call them out, and while I hand this to you.
Okay. All right. Okay.
I figured it out.
There you go. You got it. Okay.
No, just there, just there. So.
Okay. I'll wait. Okay. They're all excited. And you're going to click. Okay, great. So our first one is Novorox. First of all, I'd like to say it's 30 seconds, so you can't breathe. It's like a sprint. No, just
Tell Brad Treat's story about actually doing the elevator.
I haven't heard that story. No, he should tell it. I don't. Oh, he left. That's right.
Some competitions, they actually
Yep.
have you be in an elevator.
That's right.
This is literally, hi, I'm Brian Bauer. What do you do? Let me tell you what I do.
Okay, so good. So first we have Novorox, and I just want to say on deck is Charge CCV. All right. So we'll ready to go.
Well, thank you. My name is Philip Hutton. I'm Technical Director of Novorox Technologies. Novorox Technologies is a green reforming company. We take dirty flare gas that comes out of the ground with oil and we convert it to clean natural gas to be used at the well site, either to power the well site or to power natural gas vehicles. When a company drills for oil, combustible gases flow out of the ground with the oil. When possible, they ship that to a separation plant, but when they can't ship it, they have to flare it. The problem comes in when state and federal government puts regulations saying that they have to recycle that flare gas. They don't have a viable technical solution. Novorox Technologies provides that solution. Thank you.
Hi, myself Shailesh and Mark here. We are from Charge CCCV. We are commercializing a new chemistry for lithium-ion batteries. The USP of the batteries is a new chemistry designed for a specific niche application. And we have been able to synchronize the local infrastructure and have been producing these batteries locally here in Southern Tier. The size you see is designed for a niche application. And we expect to have these batteries in market that will make them very, very compatible with solar and wind, especially. That's it. Thank you.
Very nice. So up next is Ambus, and on deck is Chroma Nanotech.
Hi, good afternoon, everybody. My name is Mei-Ling Loco, and I'm the CEO of Ambus Technologies. So today, buildings like the one we're in consume about 40% of the world's energy, with over half of that spent on conditioning our indoor environments. So that really means 20% of all our energy is going into drying air, cooling it, heating it, and pumping it across large distances in buildings. Ambus Technologies is essentially a building company that takes waste from agriculture, upcycles it into clean panel technologies, and we marry it with sophisticated low-energy airflow control technologies in order to remediate indoor air. Our hope, particularly in the Southern Tier, is to partner with disruptive bioresin companies and leverage the agricultural byproduct ecosystem in order to deliver to our clients beautiful material systems that can reduce building energy consumption by about 30%, and all at the while delivering healthy, clean indoor air. Thank you.
Okay. So Chroma Nanotech is next, and on deck is DataArcs.
Good afternoon. I'm Dr. Bill Bernier. I'm CEO of Chroma Nanotech. We manufacture optical materials which are incorporated into passive solar treatments for windows. We let the light in, all of the light in, and keep the heat out. Thank you.
Okay, great. Okay, DataArcs. Up on deck is Ecoelectro.
So DataArcs. Hi, I'm Tomer from DataArcs. So today there are 75 million data center servers around the world, and they consume 3% of the global power production. A typical customer has tens of thousands of servers that are so difficult and time-consuming to tune that they just leave everything at inefficient default settings. Our software tunes these servers, permitting these data centers to save $62 in their energy bill per server and improving their performance. So with the help of 76 West, we will hire Southern Tier engineers to drive our successful beta launch with the 10 beta testers that represent a $5 million revenue opportunity for us. Thank you.
Okay, great. So Ecoelectro is next, and Heights is on deck.
Good afternoon, everyone. My name is Gabriel. I am the CEO and co-founder of Ecoelectro, and we make polymers. We make polymers that allow you to remove platinum from electrolyzer and fuel cell systems. As you might imagine, this dramatically reduces costs and increases adoption incredibly. Thank you so much.
Okay, Heights is up, and Best Tech on deck.
Good afternoon. My name is Russ Hannafin. I'm a Senior Vice President of Heights Energy Storage. Our company has a breakthrough technology in energy storage. We take electrical impulse from wind, solar, or directly off the grid for load control. We convert this energy to heat, and upon demand, we convert it back to electricity. Our process is 100% green and extremely cost efficient. When you think of energy storage, reach for Heights.
Okay, Best Tech up, and Clear Cove on deck.
Hi, my name is Fernando, and I'm the CEO of Bestech. So lithium-ion batteries can be better and need to be better. BAE, back me up here. So we work on making better lithium-ion batteries. And we do several things. One is we improve the performance of them, give them more energy, and make them charge faster. But we also work a lot on the manufacturing so that we can take cost away on fabricating the cell. And the third thing that we do is we do this with very interesting nanomaterials that are more friendly to the environment and completely recyclable. And our objective is to come here to Binghamton and set up a good operation here and start innovating in batteries here in the Southern Tier. Thank you.
Great. So Clear Cove is up with LC Drives on deck.
Good afternoon. My name is Alex Wright. I am the Technology Solutions Manager with Clear Cove out of Rochester, New York. We have a patented wastewater treatment technology which significantly reduces the energy consumption of wastewater treatment by about 50%. It produces reuse quality water, and the byproduct of our process produces about 200% more methane gas when fed to an anaerobic digester. We have multiple installations in the food and beverage industry. And in relation to the Southern Tier, we'll have our first municipal installation in 2016 in the Southern Tier, just in the village of Bath, New York. Thank you.
Okay, LC Drives up, and Bioenergy is on deck.
Hi, my name is Russ Marvin. The world is changing in the way that energy is converted. You now have vehicles and electric buses that run with an electric motor. Wind turbines have multi-megawatt generators in them that convert rotational energy into electrical energy. All of this is done today with technology that hasn't changed a lot in 50 years. Motors, most motors in many industries are using induction motors that were invented by Nikola Tesla 100 years ago. LC Drives has developed motors that are smaller, more efficient, and aren't at a cost premium over existing solutions. Thank you.
Great. Okay, Bioenergy's up with Standard Hydrogen on deck.
Hi, my name is Adrian Cosma. I'm the co-founder of Bioenergy. And I'm excited to tell you about our patent pending technology that it's an equipment that's a drop-in unit for wastewater treatment that is able to increase the treatment capacity by 500% and reduce the energy demand by more than 60%. Thank you.
Okay, Standard Hydrogen up next, and Applied Biorefinery on deck.
Hi, I'm Paul Motolo, co-founder and CEO of the Standard Hydrogen Corporation. We want to be your next ExxonMobil. We want to be your next Sunoco. Except the car that you will drive, or that might drive itself, into one of our refueling stations will be battery electric or hydrogen fuel cell electric vehicle. We're building stations starting next year here in New York State hopefully with the first ones here in the Southern Tier, Ithaca and Binghamton. We're doing this now by serving not only the needs of those automobiles in the future, but the needs of the grid today. We do this ecologically, economically, simultaneously. Thanks.
Okay, Applied Biorefinery, and on deck is live traffic data.
Good afternoon, Joel Howard. About Biorefinery Sciences is commercializing a cost-effective technology to extract chemicals and materials from plants using a water-only based process. And these chemicals and materials can be used as substitutes for manufacturing products that we use that are now based on fossil fuels. So that's one.
Okay. I don't know what happened to the lights. Hang on just a second. They're going, who's playing with the lights?
Hi. Maria Verardi at Live Traffic Data. No waste time anymore at the traffic lights. Live Traffic Data is enabling vehicle to infrastructure communication. We install hardware and software, traffic cabinets, and we collect data, provide this data to the traffic engineer. They are able to retime the traffic sequence, and they allow us to drive in a more relaxed manner through the intersection. Then we collect this data, we sell the data to the connected worlds, mapping and navigation, automotive, telematics, usage, basic insurance. So we allow you to drive in a more relaxed manner in future. That's Live Traffic Data. Thank you.
Thank you. Okay, I think that was it. That's great. Great pitches. I think we could have done that in about a 15-floor elevator. Right?
Yes, we could have.
I think so. Okay.
So, yes, questions? Yes. Let me answer your question. So, first of all, there will be human judges, several of them, tomorrow looking at the semifinals. There's 6 criteria, 2 that I'll speak about at some length. First is very much about clean energy impact. And so does the business actually have an impact, scalable impact? And so that's at one end of the spectrum. The other end of the spectrum is economic development in the Southern Tier in New York State, and it's the general viability of that business to create jobs or to create economic activity. And so the judges have a tough job. I can envision a scenario where there's a business that's a moonshot, that's if it were to succeed, could make a huge impact, but the odds might be long, and maybe other aspects of the business seem early stage and aren't as ready. And they're comparing that to a business that might be much lower risk, perhaps further along, but the impacts may be less exciting. But they'd say, well, that's great. That company will clearly create jobs. So they're going to have to trade those things off. We have the technical answer to your questions. We have a rubric. We have panels of judges evaluating those things. They're evaluating other things like the technical viability, the business model viability, the team, things of that nature. And so all of those things matter, but it is also, there's a subjectivity to it because you're going to be comparing some apples and bananas. You just heard 14, I think it's maybe 15 fascinating 30-second pitches out of 24 businesses. And it's very difficult to compare a highly efficient wastewater treatment process to a business in the battery space to a business that's in agriculture. So it's going to be tough, but that's what they're going to try to do. Other questions? Is anybody excited about clean energy in the Southern Tier? Yeah. Woo! Thank you very much. Laura, I think I'm going to put a plug in that there's going to be a reception. Why don't I let you do that? Reception next door.
Just congratulations again to all the semifinalists. Thank you to our speakers today, BAE, Stan, Kaiming, I think had to leave us, and Dr. Samakia. You saw when you were on break the wonderful food display we have set up out there. So please feel free to help yourselves and have a great evening and good luck to all the teams.